Have you ever watched a truck collide with a car or seen billiard balls scatter across a pool table? It looks like total chaos, doesn't it? But what if I told you that behind it all, there's one single, elegant rule, a fundamental law that secretly governs every single collision in the entire universe?
So, what is it? What is this one universal law that's in charge of everything from planets orbiting the sun to a simple game of pool? Well, today we're going to crack that code, and the answer is actually simpler and way more profound than you might think.
All right, let's kick off our investigation. We're about to put a name to this incredibly powerful rule, this principle that brings a perfect, predictable order to what looks like random chance.
And here it is. It's called the law of conservation of momentum. Yeah, I know, it's a bit of a mouthful. But trust me, stick with me on this one, because once you really get this concept, it will totally change the way you see the physical world.
So, we have the name, which of course leads us to the next big question. What in the world is momentum? Before we can get why it's conserved, we've got to figure out what we're even talking about in the first place.
You can think of momentum as the oomph a moving object has. It's really that simple. As you can see, we calculate it by multiplying an object's mass by its velocity. And this is kind of cool. It means a really heavy truck moving slowly can have the exact same momentum as a light little car that's moving super fast.
This right here, this is the absolute heart of the law. In what scientists call a closed system, which just means no outside forces are messing with things, the total amount of momentum always stays the same. It can't just vanish into thin air, and you can't just create it out of nothing.
So, if it isn't created or destroyed, where does it go? Well, it gets passed along. The best way to picture this is to think of a relay race. One runner hands the baton to the next. The baton itself doesn't disappear or change, right? It just changes hands. Momentum works the exact same way in a collision.
All right, now for the really fun part. We're going to prove this whole thing. We're going to take that classic example, a truck hitting a car, and use some math that is, believe it or not, pretty straightforward. Don't worry, I'll walk you through every single step.
See, any collision, and I mean any collision, can be broken down into these three simple phases. First, before anything happens, each object is just moving along at its starting speed. Then, for a split second, they hit, pushing on each other. And finally, after they bounce off, they move away with totally new speeds.
So let's set the stage. We've got our truck, its mass is m1 and its starting velocity is u1. Then we have the car, with mass m2 and starting velocity u2. After they smack into each other, their new speeds are v1 and v2. That's it. Those are all the pieces we need for our puzzle.
Okay, so where does this whole conservation thing even come from? It's not magic. It's actually a direct result of one of the most famous principles in all of physics, Sir Isaac Newton's third law of motion. You definitely know this one.
For every action, there is an equal and opposite reaction. Simple. So during that crash, the force the truck slams into the car with, we'll call it F1, is perfectly equal but in the opposite direction to the force the car slams back into the truck with, F2. That little minus sign you see in the equation, it just means opposite direction. That's all.
Okay, now we also know from physics that force is basically the change in momentum over time. So when we plug that idea into our F1 equals negative F2 equation, we get this thing. I know it looks a little messy, but the next step cleans it all up beautifully.
So here's the crucial insight. The amount of time that the truck and car are actually touching, that little t, is the exact same for both of them, right? And because it's on both sides of the equal sign, we can just get rid of it, cancel it out, and just like that, our equation is much friendlier.
From here, all we have to do is a tiny bit of algebra. We're just going to shuffle things around a bit. We'll group all the before stuff on one side of the equation and all the after stuff on the other. And when we do that, we get the beautiful final proof.
And there it is. Look at that. On the left, you've got the truck's starting momentum plus the car's starting momentum. And on the right, the truck's final momentum plus the car's final momentum. And that equal sign in the middle, that's everything.
What that equation is telling us, plain and simple, is this. The total amount of oomph in the system right before the crash is exactly equal to the total amount of oomph right after the crash. Nothing was lost, nothing was created. It was perfectly conserved. The math proves it. So, we just proved it for a truck and a car. But what does that really mean for, well, for everything else?
This isn't just some rule for traffic accidents. This is a rule for the entire cosmos. Think about it. A rocket works by shooting gas backwards, that's momentum in one direction, which propels the rocket forwards with an equal and opposite momentum. Planets stay locked in their orbits because they're conserving something called angular momentum, which is a close cousin to what we've been talking about. And yeah, every single shot in a game of billiards is a perfect, tiny demonstration of momentum being passed from one ball to the next.
But you know, to really understand a rule, you have to know when it applies and when it doesn't. The law we've been talking about has one really important condition. So let's end this with a question that kind of pushes us to the next level of thinking.
The law of conservation of momentum is perfect inside a closed system, where there are no outside forces like friction or air resistance interfering. But in the real world, those things are always there, aren't they? So what happens then? What do forces like friction do to the total momentum of a system? Well, that's where things get even more interesting. But that is a story for another explainer.